Good morning. Hi, as he said, I'm Brian Trammell from the CERT Network Situational Awareness Group in Pittsburgh, presenting from NetFlow to IPFIX, which is a presentation on behalf of myself and Elisa Boski from Hitachi Europe. So the question I'll be answering in some detail this morning is, what is IPFIX? It's the emerging IETF standard for exporting flow data from routers or other metering processes. So if you have like white box collectors or stuff, exporting flow information on your network. What it does define is a rich, easily extensible information model. So it's all about extensibility. It's all about not defining a single data model for flow export and a single method for flow export, but a way to define these using a template-driven data representation. And it's a unidirectional push-based protocol for exporting this flow information over a variety of transport protocols. Pretty much everyone here knows what flow data is, like NetFlow and stuff like that. Yeah, okay, good. So what it doesn't define, and this makes it different from a lot of the other flow export protocols and methods out there, are specific requirements for flow assembly. It's not an implementation of a flow assembler. It doesn't define flow key selection. It is a general representation and protocol for moving this data around. So keep that in mind when we talk about the implementations a little bit, that it is the implementations can each have their own sort of sets of requirements, and they can use IPFIX to meet those requirements in flexible ways. So the history, we've been doing this for a while. The working group started in 2001 to define a standard flow export protocol, looked at a lot of the various work that was out there, issued requirements, and then selected Cisco NetFlow version 9 as a basis for the new protocol. So V9 is essentially just an evolution of Cisco NetFlow. The biggest change is the addition of templates for flexible data definition. So instead of like with, say V5 and V7, where the data representation is defined as part of the protocol, here is your record format. This allows in-band definition of the data. So it's like, okay, here's a description of the flow records I'm going to send you. Here are a bunch of flow records. So then, yeah, the protocol was developed from the basis to meet those requirements. There are some questions I hear a lot in the community is, well, what level of compatibility is there between IPFIX and V9? Because one was directly evolved from the other. The information models, the sets of data elements you can export, are kept synchronous so that the IPFIX information model is a superset of the V9 information model. Like all the little information element numbers are the same. But otherwise, you can't just send V9. You can't export V9 flow data to an IPFIX collector and expect it to work. You do have to do some message translation. Okay, so how does this work? I say in-band definition of data. So an IPFIX stream is split into messages. Those messages can contain essentially template sets or data sets. And the data sets refer back to the template sets. So a template set will say, okay, the record type of this type has this information element followed by this information element followed by this information element, and so on. And then the data set will say, here are a bunch of records of type, and then a number that refers back to that template. So the templates essentially are in band, so there's no out of band configuration of the data models or the information model that's being exported. Which allows quite a lot more flexibility with respect to what you can export. So I say information model a lot. What do I mean when I say information model? The information model is a set of information elements, a set of fields that you can put in these flow records. So most of the usual suspects are here. You've got your 5-tuple for both V4 and V6, the various standard counters, basically total and delta octet packet counters. All of the various packet treatment stuff you're familiar with from, say, V5 or SFlow. Various detail counters, you can do sum of squares. There you can count the occurrences of flags in a stream, like so specific TCP flags. Pretty much any ICMP, TCP, or UDP header field. And then some sub-IP information for various layer 2 stuff, VLANs, MPLS, though you put the MPLS label stack in the flow records as well. The flow keys, that is what defines whether something goes into one flow or another, is not limited to a specific set of information elements. This is kind of new too. it allows you to do lots of sort of aggregate stuff. So you could say export an aggregate where the flow key is only the source IP address, and you're just counting packets and records, or packets and octets from that source IP address. So in other sort of flow export, you have to handle the aggregates differently. This can be done in band in IPFIX. So the information model itself is extensible. It's an IANA registry. You essentially go to IANA, the ITF, and have new information elements for public use. There's also a mechanism for private extensions. These are useful. I've used them myself in implementations for piloting new things before going to IANA. They're also useful for, say, if you're a vendor and you have some information you'd like to export from your exporter to your collector that's commercially sensitive. You can still export information that any other collector can interoperate with you on other than those private information elements, and you have your own private definition. So a couple of nanogs ago, I think, there was a presentation much like this one on SFlow. It was asked, okay, well, what's the comparison to SFlow? Well, SFlow is intended for many of the same applications as NetFlow and IPFIX, but it's a packet sampling protocol. So there are big advantages to this on the router. Reduces your state overhead on the measurement device. There is a mechanism sort of in the IPFIX family of protocols called PSAMP that does pretty much the same thing. It allows you to do selected packet sampling, and then it uses the IPFIX, sort of the protocol itself, with defining new flow keys to export that sample packet data. So both SFlow and IPFIX provide flexible export, like you're not tied to one specific type, data type that you're exporting. SFlow does this at the message type level, so there's a little header that says, okay, here's the type of message or here's the type of data in this message. While IPFIX does it essentially at the field level, so you can define new message types on the fly. Okay, so where are we? It has taken a bit longer than we thought. A lot of standards efforts do. The core protocol documents were essentially completed last year. They're probably to be published as RFCs this year. The working group at the ITF is continuing. We're defining extensions to and applications of the protocol. So for the most part, the early work was focused on getting the protocol right. Now we're working on, well, how can you use it, especially sort of on the collector end. And implementations tracking the draft standard are available now, and we'll talk about those a little bit later. So I'm going to go over three of sort of the most done extensions at this point. One is bidirectional flow export, putting information about flows in two directions, like a single communication, into a single record. This is useful for a few use cases. Data reduction, you don't have to re-export your keys. You can separate answered traffic from unanswered very quickly just by looking at the template ID that's on the record. And it works for full reconstruction of TCP sessions. Now, this wasn't in the protocol to start. There was no direct support for single record export of bidirectional flows. If you had bidirectional flow information at your collector, you'd have to export two records in a row, one for one direction, one for the other. This is largely because the working group was concerned with export from routers, and when you're doing asymmetric routing, when you don't know that you'll see each packet, putting direct support in for biflows may not make much sense. But we're moving into also essentially collectors or meters that are lower in the network, so maybe at the subnet or the multi-subnet level. And when you can see all of your packets in both directions at the meter, it makes a lot of sense to do that matching earlier rather than later, hence this extension. Basically, the way it works is it allows you to take any information element in the information model and say, okay, well, this may be, say, sort of your forward count of octets in this flow, and here's the reverse count of octets in the flow. So you basically, to represent a biflow, you just take your flow key, and then you have two information elements for each record, one for each direction. And that should be published in RFC this year. Another this also works for data reduction called reducing redundancy. This is essentially a mechanism for sort of foreign key references in IPFIX. You can say, Here's like a set of properties like, say, a source and destination IPv6 address, which in each flow record would take up 32 bytes. And you can assign it a 32-bit number. You export the sort of that IPv6 address pair, and then anytime that pair appears in the stream, which in the record stream, you just give it this this common properties ID that refers back to it. It's really a general purpose mechanism for doing that sort of thing. And it's focused largely on bandwidth saving information export. It's especially useful when you're dealing with large information elements like IPv6 addresses. That'll also be published as an RFC this year. So one thing we're looking at right now in the working group is that the world, many workflows out there in the world are still very file-based. Like you may have this gigantic database that has a lot of your network measurement data in it, but when you're doing a specific study or handling a specific incident on the security side, you'll take some subset of this flow data, put it into a file. Files are, I mean, we're really good at working with files. You can make them available for download. You can email them to people. You can put names on them. You can encrypt them. You can compress them. And it sort of, in dealing with flow storage, there's already a de facto standard for dealing with, and that is anyone who's using NetFlow v5 just takes the NetFlow v5 PDU, serializes them to disk, and boom, you have a file. So the problem with this is it's not extensible for data fields that aren't in NetFlow v5. So we're proposing to essentially use the IPFIX message format as a basis for a file format. Has several advantages. You get the extensibility, the self-description. It's in a lot of use cases it makes more sense than say taking all your flow data. It certainly makes more sense taking all your flow data and sticking it in XML, because you get the same sort of self-description that you get in an XML document, but since flow data is not nearly as semantically varied, you don't want to pay the overhead of XML. This, of course, also makes sense to in a IPFIX collection infrastructure. You can essentially, I mean, we're proposing to do essentially the same thing that you do with v5 PDU files. So you can make a very, very simple exporting process just by taking one of your files and netcatting it out of port. And you can do the same thing with netcat to make a collecting process to pull in. So yeah, basically an IPFIX file is just any serialized stream of messages. You can think of it as a file transport for IPFIX. IPFIX runs over TCP, runs over UDP, runs over SCTP, and this is just a fourth sort of transport layer for that. There's a set of extensions in the draft for noting the contents of a file. So if you have a lot of files, you can search through them very quickly without having to sequentially scan them. Various error detection and recovery schemes, especially if you're taking large amounts of flow data, storing it on a disk for a long period of time. You want to know if something's happened to it. And then some extended type information for these enterprise-specific information elements. So if you have if you've defined your own information element for, say, pilot use, in the protocol right now, there's not really a method for saying anything about the type information. You can just say, okay, here's a chunk of octets over here. It represents some information element. I'm not going to tell you anything more about it. You can't do anything with it. So this doesn't work as well for a couple of situations. One of those is you define an information element, you store a bunch of data, you come back to it 2 years later, you have no idea what it is. So this actually is in a separate draft now. This has been split out, and we're thinking both of these will be published as RFCs next year. So, status of implementations. There are quite a few open source implementations out there available. You can go play with them today if you like. One is done by CertNetSA, my own organization. The YAF Silk Stack. So YAF stands for Yet Another Flow Meter. I apologize for the acronym. I needed to call it something in this version repository about 2 years ago, and it's stuck. So it takes packets from the wire or libpcap dump files, turns them into IPFIX files or IPFIX messages, and does support bidirectional flow export. So this is sort of an area that has been tracking the draft standard as it's been evolving. And this feeds into the Silk, System for Internet Level Knowledge, which was originally a large V5 collection and storage and analysis tool set. pretty specifically focused on using NetFlow data for security analysis tasks, but can also be used for traffic engineering. It supports V5 and now IPFIX flow collection, and it can also, you can use the analysis tools to directly analyze IPFIX files by translating them into the Silk native format first. It's all documented on the website. And then there's a library underneath this that's used by both of them that's sort of our IPFIX implementation, and that's available from tools.netsa.cert.org. So there's also OpenIMP by Fraunhofer Focus. It provides metering processes, export and collection, analysis tools. It's a whole stack. It's as compared to Silk, which is sort of addressing security problems, is specifically focused on active and passive quality service measurement. And that's available at www.ipmeasurement.org/OpenIMP. And that uses libIPFIX, which is another IPFIX library, another independent implementation that's available from meteor.focus.fraunhofer.de/libIPFIX. That's the one that's used by OpenIMP. There's also the Versatile Monitoring Toolkit, provides metering processes, export collection, monitoring tools. It implements IPFIX and PSAMP, available from vermont.berlioz.de, and also INTOP, acts as an IPFIX collecting process, available from intop.org. So, wow, I went through that pretty quickly. Got plenty of time for questions. In conclusion, IPFIX, emerging standard, flexible flow export, representation, and storage. For those of you who want to follow the progress, want to get into the details and the IETF, you can look at these two URLs. And there are implementations available now. We've done interoperability events essentially as the standards have been solidifying. We've done 3 so far in July of 2005, March, and November of last year. So questions come up, ask now or later. Our email addresses are up here.
I see lots of collector implementations. Do you have any router vendors signed up to use this?
As it's I do not work for a router vendor, so I'm not going to make any statements on their behalf. But I will say that this is the natural evolution of NetFlow v9, and leave it at that. So yes, when, no one knows, I can't say.
I have a question way over here. Way over here.
Oh, hey.
Actually, kind of a comment and a question. The first couple of slides I saw that as the effort started in 2001, and I think I remembered that. Mm-hmm. I got to commend you on your patience if you were involved that long. It seems to be this sort of seems to be endemic to the IETF in many instances of protocol development now. It just doesn't seem like it should take 6-7 years to build a spec for something like NetFlow, and at 65 pages. That's pretty long. That's almost as big as a TCP spec. What is it that? Where's this going wrong? There's 26 revisions. I mean, what can we do to improve this? Is the IETF failing us so dramatically now?
That's a bigger question, but we have time, so I'll address it. First of all, I don't deserve any particular kudos. I've only been doing this for the last 1.5 years, so I'm sort of new blood. Oh, no, it's been 2 years. Okay, maybe a little bit. Anyway, yes, that is a problem. Absolutely. One of the issues I think you run into is there's a lot of squabbling in protocol design, especially when you have one community of people who are primarily focused on the export side, on the generating writing the protocol, and another group of people who are focused on the import side. So there was a lot of going around and around and around about that, and not very much just saying, okay, yes, we're going to do it. And I mean, I have kind of mixed feelings about this because you want to get it right, right? Of course, you don't want to get it right in 2014 when no one cares anymore. So it is a balance to strike. Some working groups do it better than others. Some don't do it at all. As far as like what policies I personally would implement, I'm not certain. That's a longer discussion, and we can certainly take it offline. But anyone else? All right, thank you very much.